One of the algorithms that people consider to be very efficient is a binary search algorithm. It is a way to find a specific item in a sorted array. So it is very efficient, it is very fast. We'll talk about time and space complexity later, but there is one catch: the array has to be sorted. So what's actually a binary search? Well, think of a common party trick. When you're trying to guess a number in the fewest tries possible, and with every guess, you are told that your guess is either too low, or it's too high, or it's correct. Suppose you start guessing like this: 1, 2, 3, 4, etc. And if you were to guess number 57, for example, it would go like that: 1, too low, 2, too low, 3, again, too low. This is a simple search. With each guess, you are eliminating only one number, right? And in this case, the number is 57, and it would literally take you 57 guesses to get there. So to make it more efficient, we will need a binary search. And with binary search, you make a guess in the middle, such as 50 here. And based on whether the actual number, 57 in our case, is higher or lower, you eliminate half of the remaining numbers. Here it will be everything that goes before 50. So we keep dividing the range in half with each guess until we find the correct number. So here's how we go. 50, that's too low. So our new part will be from 50 to 100. And my next guess will be the middle. So 75. 75 is too high, right, for my 57. So I divide it again, right? And then I keep dividing the range, and my next guess will be 63. And 63 is too high, and my next guess again will be the half. So 57. The same would work with looking for a word in a dictionary. If you want to find the word poetry, for example, you won't start from the very beginning, right? You instead open the dictionary somewhere in the middle and compare the word that you will find there with the word poetry. And if the word you see is before poetry alphabetically, you'll continue searching in the second half of the dictionary. Otherwise, if it's after poetry, you'll search in the first half. And you repeat this process, dividing the remaining portion in half each time until you actually find the exact word you were looking, or the exact number in the case with the game. By dividing the search space in half, at each step, binary search quickly narrows down all the possibilities, making it efficient even for very large lists or arrays. Let's take another example with a dictionary, with quite a lot of words. 262,144 words to be exact. And compare how many steps it will take us for a simple search and a binary search in the worst case scenario. So your simple search can start with 262,144, 262,143, etc., etc. And it actually can take you that 262,144 steps if the word you're looking for is number 1 in the book. But with binary search, it's going to be different, because with each step of binary search, you cut the number of words in half until you're left with only one word. So we'll start as we did in simple search with 262,144, and then we have a half. 131,072, and then again a half, and a half, and a half, and a half, until we come to number 1. And how many steps it will take us? Only 18. So binary search will take only 18 steps maximum, and that is a very big difference. And in general, for any list of n, binary search will take us log n to run in the worst case. whereas simple search will take us n steps. Now let's see how to write binary search in code. The binary search function takes two arguments, a sorted array and an integer target, and it returns an integer representing the index of the target value if it's found, or -1 if it's not. And we need to keep track of the left and right boundaries of our array, so we initialize them at the very beginning. So at the very beginning, left boundary is set to 0, and that will represent the leftmost index of the array, so that part. And right is set to len array -1, representing the rightmost index of the array, so here and here. And our search will continue on one condition: when left boundary is less or equal to the right boundary. And as it is binary search, and we remember that we always cut in half the array, yeah, so we always need our middle element here, and we add right to the left, and we cut it in two, right, divide it in two. And then we check if the target value is greater than the value at the midpoint index. And if it's true, it means that the target value should be located in the right half of the search range. So we update the left boundary to the index right after the midpoint, so mid +1. And if the target value here is actually less than the value at the midpoint index, the target value should be located in the left part, left half of the search range, and we'll update the right boundary to the index right before the midpoint, mid -1. And it narrows down the search range to the left half of the array. Yeah. So when the target value is equal to the value at the midpoint index, it means that the target value has been found at the current midpoint index, so we return mid. And if the target value is not found within the array, the function returns -1 to indicate that the target value is not present in the array. Now let's look at the example that we've got. We have a sorted array, and we've got a target, integer 3. So we start with initializing the variables. We have left set to 0 and right set to len array -1, and it's gonna be 8 in this case. And we are going to enter the loop because our left is 0 and our right is 8. So left is less than right, and we are calculating our mid as left plus right, in this case 8 divided into 2, and we are going to have our first mid, which is 4, right? Now we compare our target 3, and we compare it to the value at the midpoint 4. Right, and we are checking. The target is less, so we are going here. And we are updating the right boundary to mid -1, and now our right is 3. So let's make it visible. It's going to look like that. So we don't need this part of an array anymore. And we are going to repeat the process again. So we are going to have some new values along the way. And our new right is 3. And we again enter the loop because 0 is less than 3. So we are going to calculate the new mid, and 0 plus 3 divided into 2 is going to give us 1. Right? And now we compare the target 3 to 1. And it's bigger, so we're going to recalculate left. So now our left is going to be 2. So we can change our array here. And we are going to repeat the process again. We change our left to 2, our right is still 3, and we are going to compare left and right again, right? So our left is 2, our right is 3. We are entering the loop because left is still smaller than right. And we are recalculating the mid this time. Okay, so let's have it. And it's going to give us 2. Our new midpoint is going to be 2. And we are going to compare our target 3 and our new mid and 2. Our target is bigger, right? 3 and 2 is bigger, so we are changing again the left. We're updating it to 3 this time. Okay, so we're changing our border and it's now gonna be 3. So now we've updated both borders. Our left border is 3 and our right border is 3 as well. We compare them, they are the same. So we have the new mid, 3 plus 3 divided into 2. It also gives us 3. So it's not bigger, it's not smaller, it is the same. So we now can return the element we found it and we return mid, which gives us 3. So in this example, the binary search algorithm successfully finds the target value 3 and returns its index, which is also 3. At the beginning of the video, I promised that we were going to talk about time and space complexity. So the time complexity of the binary search is going to be big O of log n, where n is the size of the input array. And this is because the algorithm continually divides the search space into halves, resulting in a logarithmic time complexity. As for space complexity of the binary search algorithm, it is going to be big O of 1, actually, since it uses a constant amount of additional space for variables like left or right or mid. And the space usage does not increase with the size of the input array, making it constant or in place. So as you can see, binary search is quite a powerful tool because it eliminates half of the remaining options at each step, making the search process efficient and fast.